This video will include the solutions to a couple of problems from section 5.9. Due to the length of the problems themselves and the amount of computational work necessary to solve them, I'm not going to be working out too many of the problems. Fortunately, we weren't assigned too many of the problems. We were only assigned 7 of them. So I'll do 2 problems. I'll work on problem number 8 as our starting point. In problem 8, we're given the integral from 0 to 1/2 of sine x squared dx. And we're told that n equals 4. Now, in the beginning of this problem, or in the instructions for this, it says use the trapezoid rule, the midpoint rule, and Simpson's rule to approximate the given integrals with the specified value of n. Round your answers to 6 decimal places. Now, it's important for us to know that if we're going to round our answers to 6 decimal places, we don't want to round our calculations to 6 decimal places because our rounding error will then impact our final answer. So they want us to start with the trapezoid rule. Now, fortunately, they don't ask us to calculate the error bounds for any of these. So we have this. This is our interval. I personally always like to lay out my interval. If I'm going to have 4 subintervals, I'm going to have 1/8. I'm going to rewrite this as 2/8. I'm going to rewrite this as 3/8. And finally, I'm going to rewrite this as 4/8. Since I'm going to be using a calculator to solve this anyway, this will let me write things down and observe any kind of patterns that exist between my values and hopefully simplify my computations. Now, it may or may not simplify them at all. Part A says use the trapezoid rule. And our trapezoid rule, remember, says, all right, we're going to be finding t sub 4 here, right? T sub 4, and that's going to be delta x divided by 2 times. And then our trapezoid rule is f of x of 0 plus 2 times, whoops, premature parentheses there, 2 times f of x of 1 plus 2 times, I did it again, very consistent, f of x of 2. So this is x of 0, this is x of 1, this is x of 2, this is x of 3, and this is x of 4. So we're going to need plus 2 times f of x of 3, and then finally plus f of x of 4. Now our delta x, right, our delta x is going to be b minus a over n. So that's going to be 1/2 minus 0 divided by n is 4. So that's going to equal 1/8 for delta x. Now, when we plug everything in, right, we're taking delta x times 1/2. So we have 1/2. We have delta x, which we said was 1/8. We want f of x of 0. Now our function is sine x squared. X of 0 is 0. I'm going to go ahead and write all of this out. So that's sine of 0 squared plus 2 times the sine of 1/8 squared plus 2 times the sine of 2/8 squared plus 2 times the sine of 3/8 squared plus the sine of 4/8. Now, that's the setup for the trapezoid rule. I'm not going to do the arithmetic. I'm not going to sit here and plug all that into a calculator and waste your time on this video by calculating an answer. We can all use a calculator correctly. So this is the trapezoid rule. Everybody in the middle is multiplied by 2. The interior points are multiplied by 2. The two end points are multiplied by 1. And we don't have to find, if memory serves, we don't have to find the error bound for the trapezoid rule. We just have to calculate this. Now, part B says use the midpoint rule, right? The midpoint rule. So in part B, you would do the midpoint rule. Now, this would be M sub 4, right? And our midpoint rule says we want delta x. Remember, the midpoint rule is just a rectangle. Each of our approximations is just a rectangle. The height of the rectangle is the average, right? So we would call this f bar x sub 1. That would be our average value here. That would be x sub 1 bar. Here we would x sub 2 bar. Here we had x sub 3 bar. And here we had x sub 4 bar. So we would have to find those values, right? We'd have to find those values. Now, the easiest way to find them is not to sit here and try to find the average of between 1/8 and 0. The easiest way, I think, to find them, especially when you have numbers like this, is just to think to yourself, okay, this is an 8, this is a 16th. Change all of these instead of 8s, change them all to 16s. This is going to be 8 over 16. This is going to be 6 over 16. This x sub 2 is going to be 4 over 16. This x sub 1 is going to be 2 over 16. So x sub 1 bar is 1/16. This is 3/16, 5/16, 7/16. But our formula, just to finish writing it out, this would be f of x sub 2 bar plus f of x sub 3 bar plus f of x sub 4 bar. Now, if we write that out, that's going to be delta x, which we found was 1/8. This is going to be the sine of, remember, x sub 1 bar is the average, so that's going to be 1/16 squared. So we're going to square that first and then take the sine, plus the sine of 3/16. So we're going to square 3/16 and then take the sine, plus the sine of 5/16 squared, plus the sine of 7/16 squared. And that answer would give us our answer to the midpoint rule. And then the last step says to use Simpson's rule, right? Simpson's rule. Now, if we again take a look at Simpson's rule. So again, I'm not going to do the arithmetic here. Step C, Simpson's rule. We're okay because n is even. Simpson rule requires that. Now, we just wrote down Simpson's rule in the last, right? In our last example, I mean, our last video, I just finished the video a few minutes ago. So we said Simpson's rule, right? So this would be S sub 4 because we're doing Simpson's rule with 4. That's supposed to be delta x over 3 times. And then we have f of x sub 0. We have our y value there. Plus, and remember, the odd subscripts, right? The odd subscripts are multiplied by 4. So that's going to be 4 times f of x sub 1 plus, and then we alternate on the evens, we multiply by 2. 2 times f of x sub 2 plus, back to an odd, so it's going to be 4f of x sub 3s plus, and then to our last one, right? Our last one is going to be plus f of x sub 4. we don't go to an even, well, it is even, but we don't put a 2 here because we go 1, 4, 2, 4, 1. That's our pattern. So if we were to do this, this would be 1/3 times our delta x, which is 1/8, times the sine of 0 plus, now technically that's 0 squared, 4 times the sine of 1/8 squared plus 2 times the sine of 2/8 squared plus 4 times the sine of 3/8 squared plus the sine of 4/8. And again, I'm not going to sit here and go through the calculations on a calculator. Make sure your calculator's in radians. And again, it says round the answer to 6 decimal places. You can't do your work rounding all of your calculations to 6 decimal places, because if you were to do that, then that rounding error in each one of those calculations would be compounded over and over and over again into your actual error. So make sure you do your calculations to more than 6 decimal place accuracy, so that when you round down to 6 decimal place accuracy, you haven't, brought the rounding error into your actual error, actual answer. All right, so that's problem 8. I'm going to go ahead and pause the recording while I erase. All right, the next problem I'm going to work on is problem 19. Now, problem 19 takes a lot of steps. It's a lot of work. I'll try to write small. I'm hoping to get it all on this one whiteboard. We'll see how we're going to do. So problem 19 says we have the integral from 0 to pi of sine x dx. Now, we know the value of that integral, right? If we integrate sine, we get negative cosine. We're going to evaluate that between 0 and pi. If we draw our graph of cosine over here, right? Cosine of pi is -1, so that would be minus, and then we get a -1 there, minus cosine of 0, which is going to be 1, and we get 2, right? Now, we knew that before we started, because I think we're hopefully at this point in our mathematical career all aware that the area under this little hump for the sine curve is exactly 2. It's kind of a mystery. It's not a mystery, it's just kind of amazing. It's exactly 2, but that's what it is. It's exactly 2. So we know the exact value for this integral. The purpose of this problem is not for us to approximate an integral that we can't find using any other technique. The purpose of it is for us to practice using our techniques and then compare how close the real value is to what we get from our techniques. So they want us to find the approximations T sub 10, T sub 10, N sub 10, and S sub 10, right? That's part of part A. So let's see what we can do here for T sub 10. Now, where our integral goes from 0 to pi, we want 10 subintervals. So we're going to split this into 10 pieces. So we're going to have x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8, x sub 9, x sub 10, right? So we want to find the width of each of our intervals. So that's going to give us delta x, right, is equal to b minus a over 10, which is going to be pi minus 0 over 10. So we have our values. This is going to be pi over 10 This is going to be, we start at 0, we go pi over 10. This is going to be 2 pi over 10, 3 pi over 10, 4 pi over 10, until we get down to here, and we have 9 pi over 10, and then finally 10 pi over 10. So if we want to find t sub 10, it's going to be our trapezoid rule, right? Just to refresh our memory here, our trapezoid rule is on page, hold on, I'm trying to find it in the book, just page 402, right? 402. And it says for t sub n, we're going to want 1/2 delta x, our delta x is pi over 10. And then we need to use the trapezoid rule. So the first step, we want the sine of x sub 0. So that's sine of 0 plus. And then we're going to need, because we're using the trapezoid rule, right? Our interior points are all multiplied by 2. So that's going to be 2 sine pi over 10 plus 2 sine 2 pi over 10 plus 2 sine 3 pi over 10 plus, and it's going to keep going like that until we get 2 sine 9 pi over 10, right? All of our interior points are multiplied by 2 plus, and then our end points are just multiplied by 1. So that's going to be sine of 10 pi over 10. All right. Now, I'm going to pause the video while I calculate this, because there's no reason for you to sit here and watch me grab a calculator and work this out, because the whole purpose of this problem, remember, is to compare what is this value compared to our known value of 2. Okay, that was tedious. I got 1.983524. Now I have a programmable calculator. I have a TI-89. That makes this a whole lot easier, by the way. And in fact, the TI-89 will do the trapezoid rule, the midpoint rule, and Simpson's rule for you. Now, on our midterm, you won't have a calculator. So how are we going to do things like this? Well, I'll figure something out. Don't worry about that. We will be using Simpson's rule, the trapezoid rule, the midpoint rule. They will be tested on the midterm. Okay. But don't worry, we'll tackle that alligator when the time comes. Now, from here, we're asked to find the midpoint, m sub 10. Oh, we have to find the error. We might as well do that right now. So the actual value minus the approximate value equals our error. So for us, that would be the actual value of 2 minus 1.9835524, and that's going to equal 2 minus 1.983524. I get for our error, so we'll call that E sub t. This is our actual error to 6 decimal place accuracy, of course. I mean, so it's approximately 0.016476. Now we're going to repeat these same steps, and we're going to do m sub 10. Now, m sub 10, we're going to need the midpoints, right? And again, my approach to doing midpoints is not to try to find 9.5 over 10 pi. Well, and that would work. I mean, you have a calculator, that'll work. Halfway between 9 and 10 is 9.5 over 10. You can write decimals and fractions together like that, but it doesn't look good. I'm just going to think of this as 20 over 20. I'm going to think of this as 18 pi over 20. This is 20 pi over 20. So the midpoint's going to be 19, right? Here, this is going to be 2 pi over 20. So the midpoint's going to be 1 pi over 20. So when we write this out for the midpoint formula, right? The midpoint formula, we want the average. Now, this is just rectangles. So this is going to be delta x, which we said was pi over 10, times the sine of our first midpoint, right? The first midpoint is going to be 1 pi over 20, plus the sine of our next midpoint, which is going to be 3 pi over 20, plus the sine of our next midpoint, which is going to be 5 pi over 20, plus, and this is going to continue till we get to sine of 19 pi over 20, plus, actually, that's our last midpoint, 19 pi over 20. Now, I did this calculation already on my calculator during the last pause. I have it written down over here on the whiteboard. So for this, I got 2.008248, which would give us our error for the midpoint would be 2 minus 2.008248, or when we subtract those, negative 0.008248. Now, when we were taking notes on Thursday about the errors for the midpoint and trapezoid rule, one of the things that we wrote down as one of our observations was that they were going to be opposite in sign, and they are. The trapezoid rule error is positive. The midpoint error is negative. We also said the midpoint error is approximately half of the trapezoid error. Approximately, it's not exactly half. This is 0.16. Half of that is 0.008. So those rules that we wrote down about the errors, we need to know those, right? Those are going to be tested on the midterm. We need to know those. But they're backed up by our calculations here. Now, from here, the next thing they want us to do is find S sub 10. Now, Simpson's rule, right? Simpson's rule said, remember, we wanted to take 1/3 times delta x, which we decided was pi over 10, times, and then it's f of the first endpoint, so that's sine of 0, plus, now this is x of 1, that's odd, so that's going to be multiplied by 4 sine of pi over 10, plus 2 sine of 2 pi over 10, plus 4, right, sine, because we're at 3 pi over 10, that's odd, so it's going to have a coefficient of 4, 3 pi over 10, and this is going to repeat, right? This is x of 9, that's odd, so that's going to be 4 sine. Remember, this is symmetric, so it's 1, 4, 2, 4, 2, 4, 2, 4, 1, right? So 4 times sine of 9 pi over 10 plus 1 times sine of 10 pi over 10. Now, again, I did that when I paused the video last time. So what did I get for that? I got 2.000110. So our error, our actual error to 6 decimal places. Now, these, when I said this is equal to that, it's approximately that, right? And this is approximately this. And our error is approximately equal to this. These are all approximations because we've rounded everything to 6 decimal places. Again, I didn't do the calculations to 6 decimal places, but I rounded my solutions to 6 decimal places. So our error here is going to be 2, our actual value, minus 2.000110, or 0. Well, it's going to be negative, right? Yeah, negative, because this is 2 minus that, so negative 0.000110. Now, those are our actual errors. Remember, this has some fantasy components to it. What do I mean by fantasy components? Well, I mean in real life. In real life, this would be unknown. We wouldn't be using approximation techniques to find the answer to an integral. We knew the actual value of this error here, right? This would be unknown. We wouldn't know what the real error is because we wouldn't know what the actual value is, and you need the actual value to calculate that. This would be unknown. And finally down here, this would be unknown. The purpose of this problem, besides allowing us to have all this glorious fun with this arithmetic, is to show us that the process works, right? That they want to show us that we actually get values that are close to the actual value. We have to know what the actual value is before we can illustrate for you that, hey, look, it actually is giving you a value very close to that. Our errors are very small here, and we only have 10 subintervals. Now, that's part A, right? I have some room here. I think I can fit part B down here. I believe part B asks about the errors bounds. Compute the actual errors in part, compare the actual errors in part A with the error message estimates given by 3 and 4. That's formula 3 and formula 4. So we're going to calculate the error estimates, right? The bounds on the errors using the formulas given in the book for the error bounds. Now we can write them down as we do them, okay? So we might as well start with we started here with the trapezoid rule, so we'll find the error bound for the trapezoid rule, right? Now remember, to do the error bound for the trapezoid, we need the second derivative of our function, right? So our function is f of x equals sine x. The first derivative, f prime of x, is going to be the derivative of sine, which is cosine of x. And then our second derivative is going to be the derivative of cosine, which is going to be minus sine of x. Okay, minus sine of x. Now, we need to find a bound on this, on the values between 0 and pi, because we need the bounds we need to find the bound, and we need to bound the second derivative. That's our k, right, in the formula. That's our value of k, and that k has to be true between a and b. So how are we going to, what are we going to use for our bound, right? Because remember, we're looking, right? We're looking for the absolute value of the second derivative of x. Absolute value is going to be less than or equal to k. Now, what does that give us? Well, that gives us the absolute value of negative sine x has to be less than or equal to k. Or that gives us, when we take the absolute value of negative sine x, right, we're going to get the absolute value of sine x has to be less than or equal to k. Well, sine maximizes. Sine has a maximum of 1, right? That's the maximum value of sine. The graph of sine has this is negative sine, but the graph of sine has a maximum value of 1. So our k is going to be 1. Now, when we plug that into the error bound formula, right, our formula, remember, was the error bound less than or equal to k times b minus a cubed over 12n squared. So k is going to be 1. B minus a, that's b minus a is pi. So that's going to be pi cubed. And that's divided by 12 times n squared. That's 10 squared. Now, I did this arithmetic on my calculator, and I got for an answer 0.025839. Now remember, that's as large, that's the bound on our error with 10 subintervals can't be bigger than this. Well, we know what our actual error is. Our actual error is 0.16, much smaller than this. Remember, the error bound gives you the maximum error you could get hypothetically. So our maximum error for the trapezoid rule was 0.025839. And our real error, which we would never know in real life, but we know now because of the nature of this problem, was 0.16, smaller than our bound. Now, if we try the error bound for the midpoint rule, I told you the other night in class that the key here is to remember that the formula for the error bound for the midpoint rule is less than or equal to k, same k, b minus a cubed, same b minus a. Instead of a 12, we get a 24 n squared. That's this multiplied by a half, right? Because it's the same formula, except for instead of a 12 on the bottom, we have a 24. To get from 12 to 24, we multiplied by 2. So all we have to do to calculate this is take 1/2 and multiply it by 0.025839, and that'll give us our error bound for the midpoint rule. So I'm just going to take this, divide it by 2, and I get 0.012919. Remember, this is the bound, the upper bound on our error. Our error can't be bigger than 0.12919. And our error is not. Our error is actually negative. So it's definitely smaller than that. Now they wanted us also to find the error bound for Simpson's rule. Now there's a little bit of an extension of what we've done in the past here. The formula is different. And most importantly, we don't need the second derivative, we need the fourth derivative, right? We need the fourth derivative. So we've got to continue taking derivatives here. We've got the second derivative is negative sign. So the third derivative is going to be the derivative of negative sign. The derivative of negative sign is going to be negative cosine. And then the fourth derivative is going to be the derivative of negative cosine, which is sine. So we need the absolute value of the fourth derivative, which would be the absolute value of sine x. We need our k to be less than or equal to that. The largest sine ever gets is 1. So once again, we can use k equals 1 because that's the maximum value of the sine curve taken an absolute value. So now our error formula here for Simpson's rule, right? Less than or equal to k, the k we just found here. But it's not b minus a cubed, it's b minus a to the 5th. And it's not 12 or 24, it's 180, right? 180. And it's not n squared, it's n to the 4th. The way we remember this is this exponent is 3, this is 2. This exponent is 3, this is 2. This exponent is 5, this is 4. And n to the 4th, fourth derivative, n to the 4th. N squared, second derivative. N squared, second derivative. So if we do our calculation here, we're going to get 1. We're going to get pi to the 5th divided by 180 times 10 to the 4th, right? 10 to the 4th is 10,000. So if I grab my calculator here, I have a numerator of pi raised to the 5th power divided by 180 divided by 10,000. And I get an upper bound. Remember now, this is my upper bound, 0.00170. That's as large as an error as I can generate. And our actual error is smaller than that. We have 0.001, those match, 0.001. Our error is 10. This error, this upper bound is 70. We're clearly smaller than that. Again, remember, these things are labeled unknown. We would not know those in real life. So we would be telling the person that we were working with that this value for Simpson's rule, 2.000110, is no further away from the real value of that integral than this bound right here. This would be our maximum error allowed. And in the real world, that's what we work with. And we don't often know the exact value. So we have our estimate, we have our error bound. And if our error bound can be made sufficiently small so that it is not going to be significant to whatever process we're talking about, then we can live with whatever comes out of our approximation. Okay, that's parts A and B. I don't know what could be left for part C. Oh, part C is one of those things where it says, how large should N be to guarantee that we don't have an error any larger than? Okay, so I'm going to pause. I'm going to erase the top half of this. I'll keep the error bounds down here. We're going to need those. So I'll be right back with you. Okay. So in part C, they're stipulating that we want our error, our accuracy to be within 0.00001. So our error has to be within this bound, all right? And they want us to find the value of N that we would use to calculate that. Now, we've already found the bound on our second derivative. I'm going to start with the trapezoid, right? We'll do trapezoid first. Hence the reason I was. So we have to be less than this. Our calculation here has to be smaller than that. So K times B minus A squared cubed, pardon me, over 12 N squared has to be less than or equal to 0.00001. Now we know quite a few of these values. We know K is 1, we know B minus A is pi. So we have K, which we know is 1, Kevin. We have pi cubed. We have 12 N squared less than or equal to 0.00001. We got to solve for N squared. So we'll multiply on both sides by N squared. N squared is positive, so we don't have to flip the inequality. And we'll divide over here by this. So we have pi cubed. Our denominator is going to be 12. We're going to divide by this because we're bringing it on this side. It's positive. We don't change the inequality. 0.00001. We put the N squared over here. And if we solve this, right, if we solve this, grab our calculator and work this out. So we have pi cubed divided by 12 divided by 0.00001 equals, and then we need to take the square root of that, right, to get n here. So we're going to take the square root of that. So I'll raise that to the power of 0.5, and I get 508.31 is less than or equal to n. So n has to be bigger than 508.31. Now we're talking partitions here, right? These are partitions. We can't have a partial partition. So our n here for the trapezoid rule would be 509, right? Because 500, we need at least 508.31. That means we need 509. Now I'm just curious as to whether we got it right. So I'm standing over here looking at my book. I'll just open my book back here to section 5.9, and we're doing number 509 is the correct answer. So hey, look at that, we can still do arithmetic. So that's the trapezoid rule. For the midpoint, right, we're going to do the same thing. For the midpoint, we would have the same formula, right? We'd have k, which we already know down here. We found k was 1, so we'll just skip to that. We're going to have pi cubed. We don't have a 12, we have a 24. We have n squared. It has to be less than or equal to 0.00001. We know from our arithmetic down here what we're going to get, right? We're going to get pi cubed divided by 24 times 0.00001 less than or equal to n squared. So if we do that arithmetic, right, we got pi cubed divided by 24 divided by 0.00001. And now we need the square root of that. So we'll raise that to the half power. And we end up here with 359.43 is less than or equal to n. So n is going to equal 360 for the midpoint formula. And then one to go, right? Simpson's rule. Now, we know here k is also 1. We know it's not pi cubed, it's pi to the 5th. So we're going to have 1. We have pi to the 5th. Our denominator isn't 24, it's 180. N to the 4th, that's going to be less than or equal to 0.00001. We've already done the arithmetic twice. We're going to get pi over 5 divided by 180 times 0.00001 is less than or equal to n squared. So now we'll grab our calculator, we'll do our arithmetic again. So we have pi to the 5th divided by 180 divided by 0.00001 equals, and now we need the square root of that, so we'll raise that to the 0.5 power, and we get 412.32. So n equals 413. So we'll take a look in the back of the book, see how we did on these. 5.9. And we look and we're like, well, that's not right. That's not even close. Well, no, it's not right, because this is what I've seen on tests many times. You ask students to do all three of these a lot of times on a midterm or on a test, a chapter test, and they just get caught in a rut, right? We took the square root, we took the square root, and we weren't supposed to take the square root. We were supposed to take the fourth root, right? The fourth root. Why would it be the case that we would focus on Simpson's rule as being the most, right? We said it's the most accurate. If it took more iterations to do it, more partitions to get the same accuracy as the midpoint rule. This has to be smaller than that. So we need to go back. Now, I took the square root. I can take square root again, right? So I can just take the square root of 412.32 right here on my calculator. So I'll raise that to the 0.5 power. And we get 20. Well, I'm just going to start over and do the fourth root. I think it's right, but I don't know what buttons I pushed over here. So let's just make sure we get it right. So we get pi raised to the fifth divided by 180 divided by 0.00001 enter. And then we want the fourth root, right? The fourth root of n. Well, the fourth root is n to the 1/4, so our power is 0.25. So we'll raise that answer to the 0.25, and we get, look at that. N, well, let's don't write it like that. We get 20.306. It's less than or equal to n. Now, I just showed you the first mistake students make. They do square, they do square, they do square, and they get the wrong answer. Here's the second mistake students make. They write this down, right? So over here we went up 1, right? 508, we went to 509. Because you can't have a partial partition. 359, we went up 360. Can't have a partial partition. Over here we get 20.306. And I'll write this in red because it's wrong. And you'll see students go, okay, so n equals 21. Okay, that's wrong. Simpson's rule requires an even value of n. So we have to go all the way to n equals 22. So be careful with Simpson's rule. There's two things you can do wrong when you're calculating your value of n. First, you can take the square root just out of habit. And then second, you don't round up to the next even value. All right, that concludes my, quick note on the problems involving graphs, the last two questions in the homework. I get this every year. What do I use for my values of y? Yeah, I know they don't give you exact values. So you're just going to approximate, just pick values that are reasonable based on the graph. We're all not going to get the same answer there. Okay, we're not all going to get the same answer. That's okay. So on the last two problems, just pick values that are reasonable based on the graph. Okay, that concludes this video on homework solutions for section 5.9.